Let's do it.
All right, great. So last time we talked about discrepancy, and we talked about deregular graphs. So as a reminder, what's discrepancy? It's the minimal alpha, where alpha is some value in this relationship, so that for any subsets, x and y, which are subsets of your vertices, you look at the E of xy. So this E of xy, as a reminder, this is the actual number of edges. And you subtract from that this expression d over n, size of x, size of y. This is the expected number of edges. And by expected, based upon how large x and y are, if things were purely random, whatever purely random means. That's a very subjective and delicate question. Okay, and so we have this difference. So the real goal is to say, how random are my edges placed in the graph? That's what discrepancy is trying to do. And we want to bound it. You have this square root size x, size y. Essentially think of that as an error correcting term.
Can I ask a quick question?
Yeah, sure.
The E of xy, does that count the edges, certain edges twice, or is it only counting all of them once?
So this depends on, so the actual edges, this will count edges in the overlap twice.
Okay, so it is.
So you should think of it as, I look at every edge such that I could claim that the first vertex is in x and the second vertex is in y. Well, if there's overlap, that will get counted twice because what I call the first vertex versus what I call the second vertex, is arbitrary, and so that's why it's double counted. Now you might say that seems wrong, and well, then you can make a different definition. Why do we choose this definition? Well, the same reason that mathematicians always choose definitions. What could they prove? And so that's why we chose it this way. And so we showed that by a nice relationship dealing with singular values of matrices, that this alpha is bounded by, now we didn't call it this last time, but I just want to write what we called it last time. This is sigma 2 of A, the second largest singular value of A. But because of the relationship between singular values and eigenvalues, if you think of your eigenvalues as going, say, lambda 1 is d, and I should technically order these for the previous statement to make sense. So then I can say, really, I'm looking at the sizes of the absolute values, and those will be at the extremes. So that's why I say largest of either lambda 2 or largest of lambda n in absolute value. Now, there's something we stated, but we didn't quite prove, and we hand-waved a bit, which is the nice following fact. The max of the size lambda 2, lambda n, is small if and only if alpha is small. And so in some sense there's this equivalence going on. All right, so we're going to talk about discrepancy for general graphs. And we're not going to go through and rederive things because it's very, very similar. So this is general graphs. In other words, we're not going to make any assumptions about our graph being regular. We'll be satisfied just to say, look, there's no isolated vertices. And in some sense, most graphs that you encounter tend to be not deregular. Now, when I say most graphs you encounter, not graphs that you tend to encounter in math, because oftentimes abstract graphs tend to be regular. There's just sort of structure, and structure is very transitive, and that makes things very regular. So when I talk about things you encounter, things like social networks, if you think about your friendship graphs, and you put your vertices are people, and your friendships are your edges. Well, you have professors in the department like Bernard he has very high degree. He's friends with a lot of people. And then you have me, and it's like, well, I have Bernard, you know. So very different. And so you have to take into account that things can be very different. The example I like to give in talks is the internet graph. And you can think of different websites as being vertices, and then links between sites are edges. And so you could have two websites. So here's two websites that you might know about. One is google.com, and the other one is www.funnycatpics.com. Now, when you look at both of these, from a perspective of a vertex, they're one vertex in the internet graph. So from a vertex perspective, they're equivalent. However, we all know that in terms of the internet, these are not the same importance. I mean, one of these is a major driver of internet traffic, and the other one is a search engine. And so... See?
That was good.
You always should have a good joke, you know. Every talk should have one proof and one joke. And ideally, they shouldn't be the same. So see. Hopefully, it's not the case that every semester there's one joke. I hope that we'll have more than one. All right. So the moral of the story is you have to think of different ways to say what's important. And that's where we talked about your edges, your connections, and that led us to volume. So we're going to change our definition of discrepancy. So now it's the minimal alpha, so that, similar way, for all x, y, subset of v, we have that the edges between x and y, so we're still counting the number of edges, but now we're going to look at the volume of x, volume of y, and divide that by the volume of the whole graph. And that should be less than or equal to alpha square root volume of x, volume of y. So if you still say, okay, how does this fit in with the other setting? It's the same kind of thing going on. You still have the edges is the same thing, so it's the actual number of edges. And then this volume x, volume y over volume of g, well, this turns out to be the expected number of edges. And what you're just doing is you're saying, well, volume of x, that says how many connections do I have going out to things. So remember, volume of x is the sum of the degrees. So it says how many edges are coming out of vertices in x. And then volume of y, how many edges are coming out of vertices in y. And in some sense, that's kind of what happens over here. And then you have to divide by volume of g just to sort of say, okay, and now, you know, what's the probability that any single edge would happen? You should try to convince yourself, and it's not going to take you very long, that if you have a regular graph, a deregular graph, that these definitions agree. Well, let's at least do a little bit of hand waving here. So what is the volume of x if I'm a deregular graph?
D times the size of x.
Yeah, d times the size of x. Similar, d times the size of y. And what's the volume of g?
D times n.
D times n. So you'll notice you have a D and a D and a D. Two D's upstairs, one D downstairs. Leaves you with a single D upstairs. There's an n downstairs, size x, size y. And in a similar way, volume x, volume y, okay, there's a size x, there's a size y, and you pull it out. So this alpha essentially has been scaled by D. But other than that, everything translates over. So this is actually a more general statement. Now, we haven't said there's a nice result, but there is a nice result. So my only debate is how to phrase this. Well, okay. I'll phrase it. Fingers crossed my PhD advisor doesn't watch this video, because normally, historically, I would phrase this in terms of the normalized Laplacian, but I'm not going to phrase it in terms of the normalized Laplacian. I'm sorry, fan, please forgive me. All right, so alpha is less than or equal to the max of, and okay, we'll choose, wait, no, I've already used sigma in a different way. What's a good Greek letter we haven't used yet?
Theta.
Sorry, what?
Theta.
Ah, that's a great Greek letter. Theta 1, absolute value, theta 2, absolute value, theta n, absolute value, where theta 1 is 1. Whoops, my inequalities over here are backwards. It should be greater than or equal to. I am so sorry about that. I was like, wait. I know. I am so sorry about that. Greater than or equal to theta 2, greater than or equal to ... greater than or equal to theta n are the eigenvalues of d to the minus 1/2 a d to the minus 1/2. So this is, you can think of this as the normalized adjacency. You can replace this by your probability transition matrix if you like.
Why did you write max of length? Yes. Oh, never mind. I see.
Because one of them might be the smallest.
Absolute
Yeah.
values.
Exactly.
Everything else.
Yep.
Right.
I see.
These are the extremums. Yes. All right. And turns out that, again, we have a nice fact that, now by the way, this fact here is the same proof. Because what do? Well, the only thing that you change, what's the difference in your proof sketch? So if you remember from here, our proof sketches, we had this matrix M, which we called A minus D over N J. And then we had little x equals indicator set for x, and little y is indicator for capital Y. And so what happens here is you have M equals d to the minus 1/2 a d to the minus 1/2. All right. And so that's your normalized adjacency. And then you subtract, I want to make sure I don't mess this up. I have to think about this for a second. Sorry. Okay, what's the eigenvector for the all? Okay, yeah. Okay, I got this. All right. It's 1 over volume G times all 1 vector D and all 1's vector transposed. So that's where this came from. This D over Nj was, you said, what's the eigenvector for your eigenvalue for D, and then you subtracted it off. Well, here your eigenvector for 1 is D to the 1/2 times all 1's. And you can just check, because if you multiply your d to the 1/2 times d to the minus 1/2 goes away. Then a times all 1's gets your degrees. Then if you multiply by d to the minus 1/2, you end up with the square root of your degrees, which is what you have from d to the 1/2 times 1.
Is D a number or a matrix?
D is your diagonal matrix of degrees. So capital D here. Lowercase d here is if you're D regular.
Sorry,
In the
so
green on the left, it should be lowercase.
list of eigenvalues in there?
Yes. Well, I forgot to include my little loop.
No, exactly.
So then what is, So, sorry, with the 1D1 transpose, is D a number or is D the matrix?
This D is the matrix of degrees.
So how do you multiply 1 times D on the left? The dimensions.
Maybe just have the transpose.
Do the transpose wrong?
Okay, then what it is is D to the 1/2,
Yeah,
One.
matrix.
1
1 transpose.
transposed 1 D to the 1/2. Yeah, you were right. Thank you for correcting that. Little x,
Sorry. It's not like the J matrix?
yeah, it is a J matrix now.
So shouldn't that be 1 transpose?
Um,
Because 1 transpose 1 is just a number, either 1 by 1.
1 transpose. This is why in papers it's always easy. You can find your mistakes. Little x is then D to the, oh, no, you shouldn't follow it. D to the 1/2, indicator x. Little y is D to the 1/2, indicator y. And then you just run the same argument from last time. So it's the same tool to establish the facts. All right, and there's a nice result. The max of theta 2, theta 2 comma theta n in absolute value is small if and only if alpha is small, is still true. And in particular, so I have my notes here in front of me, so at least when I copy off my notes, I hope I can copy the right number. And of course, it's just a matter of if I can find the right number. Okay, well, I saw it earlier today, so here's what you can say. So, let's see, all right, now I want to be really careful here. Yeah. Alpha is less than or equal to this max of theta 2 and theta n. Again, alpha is the discrepancy. It's the best alpha you can choose here, which is less than or equal to 150 alpha 1 minus 8 alpha. Oh, sorry, 1 minus 8 log alpha. Now you can't even read it. 1 minus 8 natural log alpha. All right. And so that's the result. Okay. Normally I wouldn't dwell on that result other than I'd say just this is true. But I just want to mention something. This right here has a special place for me. Dramatic pause. This was my first research paper, was proving that result. So, it was a good times. And I remember one of my academic siblings came up to me and said, well, one of the things that we tried to do subsequent to this was said, well, can we improve these numbers very much? And their basic conclusion was, no, not really. You did pretty well. I was like, yeah, I did. I did do well. That's right. So, okay, so that's discrepancy. Now, before we jump into quasi-random, and we might not even get to quasi-random, there is another notion that I want to talk about, and that might actually fill up our time, which is Cheeger constants. Because it has a very similar feel to discrepancy. So what's the idea of a Cheeger constant? And the basic question about Cheeger constant is how easy is it to cut your graph? And we have to be a little bit careful here, because you might say, well, that's pretty simple, right? Because what I can do is I can just find a single vertex, and I'll just cut that vertex off from the rest of it by just deleting those edges. So this is where we're after edge cuts. And so yeah, but this feels wrong, because, you know, that's not the kind of cut I want. I want like cuts where I have big pieces. So we're going to refine it, say, you know, better question. How easy is it to cut your graph into two big pieces? In particular, what we're really after when we're asking about this question is we're trying to find what you might call a bottleneck. So pictorially, we have some great intuition where we say we have something that looks like this. So we have a lot of stuff over here, a lot of stuff over here, but very little in between. And so that in between part, this is the bottleneck. And it's like, okay, cut here. That's where you want. Now you might say, okay, well conceptually that's easy to do. I just have to find the right picture. But how do you detect it? Or how can you say whether or not it even exists? Because if you've ever tried to draw a large graph, or if you've ever asked the computer to draw a large graph for you, you know, if you go into like Sage and just, okay, here's a graph on 100 vertices, show me the picture. And it says, here's a big black abstract canvas. You know, near the corners you might see some white pieces where, you know, the edges didn't cover everything. But essentially you can't see anything. Okay, so intuitively we want to say, is there something here or is there not something there? All right. So we have to decide. All right, so we're going to be talking about edge cuts. And so what's our definition? Well, so we're going to define this. And by the way, in case you're wondering, Cheeger was not a combinatorial person, graph theory person. He was more of a differentiable manifold person. And so this is a case where they said, okay, let's take ideas from differential topology and say, can we apply them into discrete settings? And so there's several cases where they have succeeded, and this is one of them. So there's a parameter, and this is called the Cheeger constant. So well, I don't know why we chose H for Cheeger, but that's what we chose. So when we're cutting, what we really think of is we split it into two parts. So we'll have side S on one side and S complement on the other side. So your set and others, everything else. So I want to say how many edges are in between. That's the size of my cut. And I already have, well, okay. So this, right now, I haven't quite got the Cheeger's constant. This is for a particular set. I wanted to talk about how do you measure how good a cut is. Okay, so now we have to say, but how good is that cut? And so this is where we get into a little bit. We're going to divide it by the minimum of the volume of S and volume of the complement of S. So the idea here is we want to have a very small numerator. Our goal is to make, if we want a bottleneck, so our goal is a bottleneck. So if you want a bottleneck, we should have a small numerator, and then we'd want to have a large denominator, because we want to have two big pieces. And so we can say that h of s, and this is what is called Cheeger's, sorry, not hs, hg, well, that's going to be the min over all s of this measurement of how good is that way to cut. So we're after the best cut. Okay, well, what can we say? Well, observation, if G is disconnected, in other words, more than one component, then what's true about H sub G? It's very good. It's zero, because you can take it into two pieces without having to sacrifice a single edge. What? That's amazing. Okay, if G is connected, then, well, H of G is positive. Now you might say, well, what if I do something crazy like I take the min of the empty set? Well, the empty set you get 0 over 0, which is undefined. So obviously we should say the empty set, S has to have something, but it can't have everything. All right. Well, okay. What's true? Well, in some sense, this is going to, I'll write down a theorem. So we'll assume G is connected. Since if it's disconnected, okay, whatever. Then let's suppose you have lambda and lambda 1 equals 0, less than or equal to lambda 2, less than or equal to lambda n. And because it's connected, I should say our eigenvalues of the normalized Laplacian. And because it's connected, we actually can state that this first one is a strict equality. So lambda 2 is strictly positive. Well, here's the fun conclusion. Then, lambda 1 is less than or equal to 2 times your Cheeger constant. And it's greater than or equal to 1/2 Cheeger constant squared. So, all right, what does this tell us? Well, it tells us...
Do you mean lambda 2?
Yes, I meant lambda 2. Sorry. There's a convention that I can oscillate between. Sometimes the first eigenvalue is called lambda 0. And so that's why all right. So the punchline here, which will sound very familiar, it'll sound a lot like what we just said for discrepancy. If lambda 2 is small, then there's a bottleneck. Somehow your graph has a cut. Whereas if lambda 2 is large, well, that says there's not a bottleneck. And so it's hard to cut your graph into two pieces. Okay, well, it would be nice if we could prove one of these. And so we'll try to prove this one. Okay, so a goal. We're going to try to prove that lambda 2 is less than or equal to 2 hg. Now to do that, we're going to need to do a little bit of sidetrack here. And we're going to need to talk about the Rayleigh quotient. So given a real symmetric, what? Have you been waiting for this?
No, but it's kind of cool.
You're like, oh, I've been waiting all semester for us to pull out the Rayleigh quotient. That's just...
Never seen this excited before.
All right, so you look at X transpose mx over X transpose X. Now, what's true is if you take the min of this, what do you get? So the min over all X non-zero. It's the smallest eigenvalue.
Is it okay to say mid here instead of feet?
Yes, because it is achieved.
Okay, cool.
And it's achieved when X is your eigenvector for the smallest eigenvalue. Essentially what happens is you can say min, because if you think about the kind of optimization we're doing, when we say min over all X non-zero, because you can scale, you can say, look, I can assume that min over all X not equals 0, norm of X equals 1. That means that you're optimizing over a n-dimensional sphere, which is closed and compact. And since it's closed and compact, you must achieve your minimum. But another way to say it is, it achieves its minimum at the eigenvector. So, all right. Well, suppose I wanted to find not the smallest eigenvalue, but the second smallest eigenvalue. What would I do? For all you fans of Rayleigh quotients out there. Sorry, what?
I don't want to stay Courant-Fisher.
Well, but essentially it's Courant-Fisher, yes.
Okay.
But it's a very simple case,
Okay.
right? So what we're going to do is we'll let y be the eigenvector. We'll go ahead and call it for lambda 1. And then what we'll do is we'll do the min over all x non-zero, where x is perpendicular to y. And then we do the same x transposed mx over x transposed x. And then because you're perpendicular to this eigenspace, well, that says the only eigenspaces available to you are the eigenspaces for lambda 2 through lambda n. And you say, all right, well, among all those eigenspaces, I really want to put everything on lambda 2 because that's the smallest it can be. So this would be lambda 2. All right, so far so good? Good, awesome. All right, now we're gonna take this idea. So, what do we know? Well, we know that lambda 2 is the min over all x non-zero. So now we're into proof mode, and I can see that I'm not going to fit it on this page, so I feel bad starting it here, but we'll get it on the next page. Okay, so it's the min over all x non-zero, x perpendicular, and let's recall, do we remember what the eigenvector is for the normalized Laplacian? Associated with the smallest eigenvalue.
Is it 1?
Ooh, it is almost 1 with a suspicious gap. It's d to the 1/2 times all ones. And so as a reminder, this is d to the minus 1/2 L d to the minus 1/2. So the d to the 1/2 and d to the minus 1/2 cancel. Then L times the 1's vector is 0 because your row sums are 0. And then once you're 0, you're 0. All right, so that's x transposed Lx over x transposed x. All right, great. Well, let's rewrite this. Okay, so what are we going to do? Well, we're going to change x. And so what we'll do here is we're going to set x equal d to the 1/2 y. Okay? All right. Not that y above, just in general. Okay, so if we follow through with this, then we say, okay, as I vary over all choices for x, it's the same as varying all choices for y, because d to the 1/2 is invariable. We'll assume our graph is connected, so there's no isolated vertices. All right, so this is the min over all non-zero y. Now, when will d to the 1/2 y be perpendicular to d to the 1/2 1?
Y is perpendicular to 1.
Yeah, we need y to be perpendicular to 1. All right, I think that's what we need. As I check my notes, well, I think it is. Okay. Is it? No, it's y is perpendicular to d times 1.
Because you have to do like the trans. You have to actually compute the transpose.
Yeah. But don't worry, we'll get what we need. All right, now upstairs we'll get y transposed. Then we'll have d to the 1/2 times d to the minus 1/2, which cancels. So we'll have an L. And then we'll have d to the minus 1/2, d to the 1/2, which cancels. So we'll have a y. And downstairs, well, we're going to get y transposed dy. All right, so far so good? So now, flashback, y transposed ly is the sum over all edges of our y sub u minus y sub v squared. And then downstairs we have the sum over all vertices, and it's going to be our degree of u, which I'll denote d sub u, and y sub u squared. Okay, how's that? Now, this is for any choice of y, as long as you're perpendicular to d times the L1s. So, we're taking a min. So now, let's think about since we're taking a min, let's pick a good choice for y. We're going to choose, but choose wisely. So, here we go. We're going to choose y. Now, think about the picture. What are we after? We're after the bottleneck. So we want to say the only thing that should matter are the edges that cross. And things that where I'm not crossing, I want to ignore. So you say, well, if I want to only see the edges, but things where I don't cross, well, that would say what I should do is I should pick something on this side, which is constant, and I should pick something on that side, which is constant. Because then what happens is if I'm on either side, I get 0, whereas if I cross, I get the difference of what I chose. So here's the idea. We're going to let y sub u be 1 over volume of S, if u is an S, and 1 over volume complement of S, if u is an S complement. So I'm picking constants here. Now, They're not just any constants. We have to check some things. So, I forgot, I need a minus sign. Because if everything's positive, this is not going to work. I'm not going to be able to be perpendicular to a positive vector. So claim 1, this vector y is perpendicular to d times the all ones. Well, how do you check that? When you do the dot product, so you get y transpose d all ones, what's going to happen here, this is really just the degree of the vertices. And so you're going to end up with the sum over all u and s of the degree u over volume s minus the sum over all u and s complement, the degree u volume of s complement. But if I add the degrees in s, what am I really doing? The sum of the degrees is the volume. One minus 1, which is 0. All right, good. Now, I don't know if there's a claim 2, but I'm hedging my bets. Because, in case there is a claim 2, I can look smart. And if there isn't, well, no one will question me because they will have forgotten it. Okay, so with this particular choice for y, we can say then lambda 2 is less than or equal to using this y. Because remember, this is meant over all y. So I just have to pick a y as long as I'm perpendicular. So we're almost there. So what happens? Well, we're going to get upstairs. The only thing that we get is the number of edges between s and s complement times 1 over volume of s plus 1 over volume s complement squared. That's what will happen upstairs. Because the only thing that counts is if they're in different sides. And when they are in different sides, it's one term subtract the other. And the number of times I count that is the number of edges. Downstairs, well, we're going to get the sum, and we'll split into two parts, u and s, and we'll have our degree of u over volume of s squared, and then we're going to have plus our sum u and s complement, degree of u, volume of s complement squared. All right? Well, what happens? This is edges s, s bar, 1 over volume of s plus 1 over volume s bar. Don't worry. I know we're basically out of time, but we'll finish. Squared. And downstairs, we do the same thing. But now it's volume of s over volume of s squared, so it's 1 over volume of s and 1 over volume of s complement. And then we're like, whoa, that's so cool. We cancel. And now we say, okay, well, the trick is, the last thing, say, okay, what can we say about this? Well, I have volume of s complement. What I can do is I can say, what's the smaller of the two? And then if I just take the smaller of the two and do it twice, so 2 times 1 over the min of volume of s complement, then I have a less than or equal to. And now at this point I say, but that is 2 Cheeger constant Hg, which is what we wanted. So the lambda 2 is less than or equal to 2 Cheeger constant. All right, if you want, I'll give you a 60-second hand-waving proof about the other one. So here's the hand-waving proof about the other one. So you have lambda 2, your eigenvalue. You have x2, which is your eigenvector. You now arrange your vertices according to your eigenvector. So in other words, you put them in a line. So you have your n vertices. So whichever is the smallest of entry x2, that's your first. Whichever is your second smallest, that's your second, and so forth and so on. And now what you do is you say, okay, look over all cuts that look like this, where you basically say everything that came before that, everything that comes after that. And you can show, it can be proven, that one of these is good. And that's how you establish the other inequality.